All right, y'all. Hello. It is I, your teacher, Mr. Cordero. Uh, I'm out here in the hospital with my little baby sleeping with his mom. But you can kind of see him in the reflection. Okay. Well, I was gonna put some videos up for this, like so that you guys could watch them, but then I thought that like it would be too like I couldn't find good videos that went along with the notes closely enough, or like a lot of people are teaching it in like 10 videos, but you could do a single video to teach all these concepts. So that's what I'm doing. Also, a quick update is that Miss S is still like the student teacher for Misty Marinas last year is still like planning to be your long-term sub. It's just a couple things. Number one, like the baby came a week and a half early, so we thought we had more time. So that's why she's not like in the classroom right now, is because you have to go through a bunch of stuff to like fully get officially hired, and we thought we had more time, and so we like weren't fully like expecting her to step in yet. So that's why she's not in yet, but she'll be there this week if everything goes well. And then the second thing is that we don't know, she's like in the middle of interviewing for this like full-time job, so we don't know if she'll be able to stay forever. But she'll be able to stay for as long as she can, hope maybe forever, but also hopefully she gets a full-time job. So I'll keep you posted on that. But now let me teach you about continuity. So let me share screen. Okay, and then I go here. Okay, and then this was me just testing. So let me delete that, and then I'll explain more about this in a second. Okay, so hopefully, first of all, the last thing, the squeeze theorem kind of made sense. If you have questions, you can email them to me, but at TBH, I don't know how much I'm going to be able to reply. But you could ask your sub, and Miss S knows the squeeze theorem. When she's there, you could ask her. But anyway. Now continuity, watch this. So continuity is this really, really, like conceptually it's a very simple thing, but it's a super important like property of some functions. So here's what it is conceptually. A continuous function is what it sounds like. Like here's an example of a continuous function. One big connected thing. No breaks or jumps or like asymptotes or anything like that. So this guy is continuous. This red example would not be continuous. So like, for example, if you had some sort of jump like this. Oh, there we go. If you had some sort of jump like that, then that would not be continuous. It's supposed to be an open dot, but it's hard to draw. Okay, so not continuous. This is continuous. This black is supposed to be a check mark. Okay. Okay, so super simple concept. A function is continuous if it's all connected. But maybe you've seen already that in this class, like simple ideas are hard to could like formalize and put into formal math. So it might be confusing what I'm about to say, but this is like the formal version of a continuous function. So here's the here's the formal definition of continuous. So, um, formally, a function is continuous where its limit and the function value are both, well, first of all, they both exist and they're both equal to each other. So in other words, f is continuous at a point c if these three conditions are met. So f of c is defined, the function value exists, the limit exists, limit is x goes to c of f of x, and then the function and the limit are equal to each other. If any one of these conditions is not satisfied, then the function is discontinuous at c. And you'll see examples of all these three things, like each of these three things being broken, and you'll see why intuitively it's not, the function isn't continuous at that point. Okay, so here's some examples. The first one says determine whether each thing is continuous at the indicated value. Okay, So that first one says it's a polynomial 3x squared minus 5x plus 4 at x equals 1. Here's me checking formally, but at the end I'm going to say something about this function that I just look at it and I like know right away for sure it's going to be continuous. But I'll save that till the end. So me checking formally, okay, I gotta check that these three things that I'm about to draw on, those three things have to be met. If they're met, the function's continuous at 1. If they're not met, then it's not continuous at 1. So here's me checking f of 1. Like, what I mean is, can I plug in 1 into the function? And of course I can, like, without breaking any rules. Here's me checking 3 times 1 squared. Sorry about my handwriting. I'm writing on a screen. It's hard to do it. Times 5 minus 5 times 1 plus 4. It's having a hard time. I'm sorry. Okay, there we go. Okay, and then I check if this is a defined number. In other words, like, did I divide by 0 or take the square root of a negative or anything like that? But obviously, I did not. So, like, this will give me a value if I were to calculate it. This is like 3 minus 5 plus 4, 3 minus 5 plus 4, which is whatever it is. It's 7. It's 2. Okay, so f of 1 exists. Does the limit exist? Well, yeah, and I would find that by plugging in the actual value. So, here is me taking the, oh my God, sorry. Here's me taking the limit as x goes to 1 of f of x. Well, I would just find that by plugging in the value anyway. But okay, here's me checking formally. That would just be 3 times 1 minus 5 times 1 plus 4. And we just found out that this is 2. So kind of a weird thing, but technically, remember, the first one I'm just plugging in the number, the second one I'm checking if the limit exists. Okay, both of these are true, the limit exists, the function exists, and they're equal to each other. The function was equal to 2 up here. The limit here in red was also equal to 2, and that was our third condition. Let me see if this likes me. Okay, I gotta scroll up a bit. All right, see the third condition here that I'm circling in this space color says that if the limit is equal to the function, then the that's the third condition, and we're good. The function is continuous. So in this case, the three conditions were met, and the function is continuous. Oh my God, I'm sorry. The three conditions were met, and the function is continuous. So yes, this dude is continuous. Okay. But the thing I was saying at the beginning is that me, with my experience as a math teacher, I see this function and I right away know that it's going to be continuous because all polynomials are always continuous. I'm sorry, my computer's freaking out, but all polynomials are always continuous, so that might be a good thing to write down. I'll try to write it down without my computer getting mad. All polynomials are continuous everywhere. Okay, cool. Okay, so in the future, you can just look at a polynomial and just say, yeah, it's continuous. You don't have to show this formal stuff unless it says in the directions, show every single step. Okay. So first one done. Second one, you're checking, are all these three things, these three conditions that I'm drawing an arrow towards, are those three satisfied at x equals 2? Okay, so let me check here in red. If I try to plug in g of 2, God. There we go. I try to plug in g of 2, and look what happens. At the top, I get 2 squared plus 9, which is 4 plus 9. At the bottom, I get 2 squared minus 4, which is 4 minus 4. And then the top would be 13, the bottom would be 0. This is not a number, like I'm dividing by 0 here. So that is not defined, so already I'm done, I can stop, because the first condition was not met. G of 2 is undefined, 13 over 0. So since g of 2 is not defined, that's one of our conditions, we can stop right there and say not continuous at 2. Cool. Or you could also say discontinuous, like it says up here in Galaxy, colored. Discontinuous. Cool. Okay. So basically, you are verifying in these exercises whether these 3 conditions are met. Again, if they're all met, then the function is continuous, but it has to be all 3. And then if one of them is broken, then it's not continuous at that point. Okay, then this says some stuff about continuity. So it says wherever a function does not meet the criteria for being continuous, we say that the function is discontinuous, like I was saying before. And any discontinuities, like any points where the function is not continuous, can be classified as removable or non-removable. So removable discontinuities, informally, we call them holes. So that's what a removable discontinuity is. It's just it's a hole. And if the problem asks you, like, find the removable discontinuities and justify that they're removable, that would be using these 2 things. So if the question asks, justify that this is a removable discontinuity using limits or using the formal definition or whatever, you would say these 2 things. So like the function has a removable discontinuity at x equals whatever because f of whatever is undefined, but the limit value at that point does exist. And I'll say this again when it becomes relevant, but for now, keep that in mind. Okay, and then like I said, removable discontinuities are just called, like, you know them as holes, but now they have this more formal name. That's removable discontinuities. My God. Okay. Okay, and then non-removable discontinuities come in 2 varieties. They are jump discontinuities, which are what they sound like. So like, for example, a jump discontinuity is this guy in green that I'm about to draw. That's a jump discontinuity. It's like when the left limit does not line up with the right limit, which is what it says here. That's formally. All right, and then infinite discontinuities, also what they sound like. They're vertical asymptotes. So whenever your function goes towards infinity, like I'm about to draw in orange, uh, okay, it's not letting me draw. Give me a second. Okay, this thing that I just circled in orange is an infinite discontinuity. And it can be like I just circled here in orange where both sides are going down to negative infinity, but it could be that only one side goes to infinity and the other side is staying at 2 or something. So as long as one side goes to an infinity, that is considered a infinite discontinuity. Okay, so example 2 here, I kind of did have the work already, but it says find all the discontinuities and classify them as uh, what they are. So removable, jump, or infinite. So here, let me erase this stuff. And then let me stay quiet for 10 seconds and let you guess what each discontinuity is, or like where they are and what it is. So here's me staying quiet. Okay. And then hopefully you noticed the following. So if this is the graph of f, then I would answer this question like this. If it lets me draw, okay. I would say this is supposed to be a bullet point. Okay, I would say f has a first discontinuity I see is this hole that I'm about to circle in black. And remember, holes have a formal name. They're now removable discontinuity. So I would say f has a removable discontinuity at x equals whatever it was. Where is that? X equals -1, it looks like. Okay, so that's the first one. Notice that the hole could be defined like in this case, there's an open dot up here and a closed dot down here. That's considered a removable discontinuity, but also look at this next one in purple. This dude right here is also a hole, even though it's not plugged up anywhere like it did. Like it doesn't have a closed dot anywhere near it. That's also a removable discontinuity. So let me just add to this black sentence. F has a removable discontinuity at x equals 1 and at wherever we just said, and at x equals whatever, 2. Cool. Okay, and then we already circled the other two, so let me go back to the original colors. We said this in orange was an infinite discontinuity because the function is going to infinity. Infinite. Sorry. At x equals 3, it looks like. And then in light green, here's a jump discontinuity. That is where the left limit and the right limit are not equal. So the function is like kind of disconnected and you have to jump from one to the other. So here is jump disk at x equals 5. And that's all this was asking for. Find out the discontinuities and classify them as jump, removable, or infinite. So we're done with this one. Hopefully that made some sense. Okay, next. Sorry, this is what I have to do to scroll for some reason. Next, it says determine if the function g is continuous at 1. If g is continuous, then classify the discontinuity. And it says to justify your answer. So this will be a good question if this is discontinuous, because you can see how you would justify it. Okay, so it says, is it continuous at 1? And notice that 1, okay, so remember how I have no idea what this looks like. I have not graphed this yet, but it doesn't really matter what it looks like. What I'm looking at is this is a piecewise function and it's split at x equals 1. So over here at x equals 1, the function's doing one thing. I don't know what. It doesn't really matter. It might be doing like little swirls to the left of 1, and to the right of 1 it's doing something else, like maybe some green swirls. And what this question is asking basically is, do these blue and green curves like connect, or are they disconnected? And then that'll tell us whether it's continuous or discontinuous. Okay. So let's check. How would I check that? Well, formally what you're doing is you are getting the left limit of g up here, and then you're getting the right limit of g down here, and you're seeing if it's the same number. Informally, you are just plugging in 1 into the top function and the bottom function and seeing if you get the same number. But here's me pretending this is on the AP test and somebody's grading it real hard. I would say something like the limit as g goes to 1 from the left of g, or sorry, I said as g, I meant as x goes to 1 of g of x is equal to, I'm going to skip the middle step and I'm just going to say it's 3 times 1. It's this top function with a 1 plugged in. 3 times 1 minus 1 cubed, which is equal to 3 minus 1 is 2. Okay, there we go. And then here's me checking the right limit. Limit as x goes to 1 from the right of g of x equals, okay, 2 times 1 minus 1 is equal to 2 minus 1 is 1. Okay, and then already I can stop and say, oh, okay, look, the left limit does not equal the right limit. Therefore, the general limit doesn't exist at 1. And that was one of our conditions. So here's me scrolling back up to the conditions. Come on. Here's me scrolling back up to the conditions. All these 3 have to be satisfied before I can consider the function continuous. Already I found one that was not satisfied. The limit part was not met. So since the limit from the left does not equal the limit from the right, that tells me that this has to be a jump discontinuity, as we talked about a little bit before. So no, g is not continuous at 1. Come on, there we go. G is not continuous. I'm sorry, I don't know why it's not letting me write at 1, or at x equals 1. And then it says classify the discontinuity. Like, what type is it? Is it an asymptote? Is it a hole, or is it a jump? In a lot of these cases, in most cases for piecewise functions, it's going to be a jump discontinuity, especially if it's split to the left of this number and then to the right of this number. But formally, how you would say that is, since the left limit does not equal the right limit, g is not equal to the right. Then I know that like this is the requirement for a jump discontinuity. So since this is not equal to this, it's a jump discontinuity. Okay, then I think that's it, right? Determine if it's continuous, done. If it's discontinuous, classify it and justify your answer. Okay, I did it. So all of this stuff in black would be your answer to this question. That would be a good formal answer. Okay. And then finally, last thing is determine and classify all of these discontinuities and justify your answer. Okay, so here is how you do this one. So if it's asking you find all the discontinuities, basically there's 2 types of questions. If it's a piecewise function like the one we just saw in example 3, then this one's probably going to be a jump discontinuity, and basically you're just checking what we checked in example 3. Does the left side equal the right side? Take the limits wherever the function is split. In example 3, that was at 1. and determine if that's the same number. If it is, then it's continuous. If it is not the same number that you get at the end after plugging in this number that I circled in Galaxy, in this case 1, if it's not the same number, then the function has a jump discontinuity. Okay, so that's one type of question. The second type of question is if you get a fraction and it's asking you for all the discontinuities. And for fraction functions, like for rational functions, that's what this is called. You're basically just looking for where the bottom is 0. And if the bottom is 0 and that 0 does not cancel, then it's an asymptote, so an infinite discontinuity. But if it does cancel, then it is a whole or a removable discontinuity. Okay, so that's what I'm about to look for here. So basically, I'm checking where's the bottom 0 and do any of those zeros cancel. So here is us doing that in pink. Okay, so first let me factor everything. That function is equal to x plus 1. Here's me factoring the top. It's a difference of squares. Over. And then the bottom factors as x plus 1 times x plus 1. Okay. And so right away, I look at this and I say, oh, well, this is kind of a bad example. That's what I say. But I look at this and I say, okay, the bottom is of this fraction is 0. Let me say like denominator. Denom. That says denom. That's a D. Denom equals 0 at x equals -1. Okay, so that's got to be a discontinuity. What type is it? Well, like I said, this is a kind of a weird question. I would have chosen 2 different factorings of this, but let me explain it in this case, and then I'll explain it in a more simple case. In this case, even though one of the zeros cancels on the top and on the bottom, I'm still left with a 0 on the bottom at -1, as in if I were to plug in -1 into x, I still get non-zero over 0 here, like a 0 that does not cancel. Like here's me plugging in -1. -1 on top, it gives me -1 minus 1, which is -2 over -1 plus 1, which is 0. And that, I guess, they would get mad if I used an equal sign there. So this is why I'm saying since I get non-zero over 0, this is a asymptote. So I'm gonna say x equals -1 is a infinite discontinuity. That's the formal word for asymptote. Infinite. Okay. There we go. Okay. And that's all it can be. So for argument's sake, let me just, because we don't have another example after this, let me just pretend that this factor that cancel was like an x plus 4. So let me change this. Let's pretend this factor that canceled was an x plus 4. Okay, in that case, then I would have at -4, because that's the number that I'd have to plug in to make this black part 0. At -4, I would have a removable discontinuity. So again, if the factor on the bottom cancels a factor on the top, in 99% of cases, that is going to be a removable discontinuity. The 1% would be in this particular case for this example, where even though it factored on the top and bottom, there was another x plus 1 at the bottom that made the -1 a infinite discontinuity. Okay, so anyway, in this case, all we have is the infinite discontinuity at -1, because even though the x plus 1 canceled on top and bottom, there was another x plus 1 on the bottom, making it an asymptote. That x plus 1 on the bottom, the second one, did not cancel. Hopefully this is making sense. Okay, so I answered this question kind of, but it says justify your answer, and that means like formally justify your answer. So the way you justify infinite discontinuities is like this. You say that it has a limit that from one side goes to infinity or negative infinity. That's the formal way to justify this. So here's me trying that. I'm going to take the limit as x goes to -1. Jesus Christ. Okay, I can't draw on this thing, but x goes to -1. From the left of that function f of x. And it looks like I would get, remember, when it's non-zero over 0, you just plug in a number real close to -1. So here's me trying that. This is me plugging in -1.1 into the top and bottom of the, I'm just going to use the simplified function. So -1.1 minus 1 over -1.1 plus 1. Remember here, I just care whether it goes to positive or negative numbers. So -1.1 minus 1 is negative. -1.1 plus 1 is also negative. And overall, this fraction is negative over negative, which is positive. So this is just going to Okay, so this limit ends up being infinity. And it doesn't matter whether it's infinity or negative infinity. Like, I already knew it was an asymptote, but for my justification, I just have to say this is an infinite discontinuity since the limit as x goes to -1 from the left of f of x is infinity. Okay, so you just show that one side of the, like, a one-sided limit approaching your value is infinite or negative infinity, and then that's your justification. Okay, so that is the lesson. Hopefully you understood some of this. Sorry about all the computer troubles and the baby crying, but come on, I just had a baby. I'm trying my best. All right, if you have questions, ask your sub or look it up on YouTube. That you'll find a lot of good videos. It's just that they're really long, and I just wanted one single video. All right, that's it from me. Good job, you guys. Hopefully you understood some of this. Do your homework and make sure that you do, and that's all. All right, goodbye.